All right, let's put those elementary regions to use, and we're going to begin to kind of develop the theoretical framework here in this video for using those elementary regions. First thing we need is to talk about the extension of a function f, and so you can see the definition in front of you. All it says is that we call the extension function the original function of f if we end up having a point that is in our domain D, okay, and if we have a point that's not in D, then it's just 0. Okay, so the real idea here is that if we have f over d, when we think about integrating that, theoretically we should have, if we look at f extension, okay, over a rectangle that contains d, so just pictorially kind of what's happening is, so here's our d blob, that's our domain, and now what we're doing is we're taking and placing a rectangle over it. Okay, and we're going to call that rectangle R, and so R contains D, and we're going to say, okay, well, anytime we land in the domain, we're going to call that f of xy, and if we land not in D, then it's 0. Okay, that's kind of the idea of the extension function and a rectangle. And then with this extension function, then we can do the integration more easily because we know how to do this. We did the rectangles last week. Okay, but now we have to be careful. We have to go through that formality. So if we have a rectangular region R that contains D, then is this extension function integrable? Okay, well, we discussed criterion for integrability last week, and we said if f is bounded, right? We have to have bounded on R, and we have to have the set of discontinuities of f has 0 area, then we can say that the double integral exists. Okay, so the first question is f bounded? And my B got cut off there, but it says bounded. And so, well, we know that here's kind of the logic string. So we know f is continuous, right? Okay. And we know that D is compact. Okay, so closed and bounded. So this is kind of criterion that we're working with, and we're assuming that D is an elementary region. Okay, so it is compact. And then these two things give us that by the extreme value theorem, f is bounded on D, okay, and then since f is bounded and really the extension function is just f, okay, or 0, right, so this implies that f extension is bounded. Okay, so yes, we have bounded, so maybe it's integrable. Okay, and then the next thing is, does the set of discontinuities of f extension have 0 area? Well, this set, okay, I don't want to write it all out, okay, is a subset, or is contained in the boundary of D, okay, so it's a subset of the boundary of D, which boundary of D is a line, so that has 0 area. Okay, so according to this, yes, it is integrable, and so then by definition we say that if f is a continuous region on an elementary region, so we have to have elementary region D, and R is a rectangular region that contains D, then we can say that the integral over D of f dA is equal to the double integral over the rectangular region R of f extension dA. Okay. So in other words, we can use the extension and region R to find our integral. Okay, and then a theorem that goes hand in hand with this is that if we have a specific type of elementary region, type 1 or type 2, type 1, we can write this as A to B, and then gamma x to delta x of f of xy, and then dy dx. Okay, and similarly for type 2 region, we can do from c to d of alpha of y to beta of y, f of xy, dx dy. Okay, and so this is kind of the framework that we're going to use in the rest of the videos, looking for elementary regions and typing them, and then using the elementary region to make our life easier in computing integrals over regions that are not necessarily rectangular.